Cool. Thank you. Good evening, everyone. Thank you guys for joining us on this really, really hot day. So I'm here to talk about how do you build observability into a serverless application, which, of course, we should start with the question of what do we mean observability, and how do we mean it different to when we say monitoring. And when I say monitoring, I tend to think of it as like a watchtower where you're watching out for those known failure modes in the system, like your network I/O going through the roof, or CPU spiking out, or you're running out of memory. Whereas observability is probably closer to what government agencies are doing in terms of monitoring and collecting lots of metadata about what's happening so that they can observe and figure out what is happening in society without actually, from afar. And in a similar vein, control theory defines observability as a measure of how well the internal state of a system can be inferred by just looking at its external output. So our applications, besides the functional things it's doing, can also have all kinds of useful outputs that we can use to help us figure out what the application is actually doing, and also when things go wrong, what actually happens, so that we can then debug the system quickly and figure out how to fix it. In terms of external output, we are talking about things like logs, metrics, traces, so that if you go back to this, probably one of the first posts that started to talk about observability, it talks about the 4 pillars of observability in terms of monitoring, alerting, distributed tracing, and log aggregation. And as we start to build more and more complex systems, we are also going to need more help in terms of understanding what the hell is going on in all these very complex and very large distributed systems. And fortunately, as people are building more and more these complex systems, tools are also starting to mature and get better. You have lots of tools in both the open source space as well as in the commercial space that's catering for people building all these very large, very complex microservices. So I think in general, the tooling in terms of the sort of general microservices world is actually pretty good. And then came about 2014 when Amazon announced the Lambda and reinvented that year. It became like an Achilles heel to a lot of the existing tools, because many of these tools work by having the ability to install some kind of an agent or daemon on your servers where they can collect a lot of information about your application. But of course, with Lambda or serverless in general, you don't have access to the underlying server anymore. So there's nowhere for you to install those monitoring agents and daemons. So in terms of who I am, my name is Yan Cui. I am an independent consultant where I help loads of different clients on their migration towards serverless paradigm. And I'm also working with Lumigo as a developer advocate. And Lumigo is, of course, one of the companies that are trying to solve this serverless observability problem. And they have a product which I'm happy to talk to you guys about later on as well. Personally, I've been using AWS since about 2009, running all kinds of different workloads in production. And as of last year, AWS also made me one of the community heroes that focuses on a serverless space, which as one of the perks that I get to go to re:Invent for free, so which is pretty cool. So that's about that. In terms of the new challenges that the serverless paradigm has introduced to our tool chain, we mentioned that, okay, with Lambda, you don't have access to the underlying operating system or the infrastructure that runs your code, which means there's nowhere for you to install many of these monitoring agents and daemons anymore. All these daemons and agents for a long time, they have served a very important purpose, and they've done their job quietly in the background outside of the critical path of your code. So if you're building APIs, these agents are running behind the scenes. They don't impede, they don't add latency to your critical path where you're trying to handle user requests and respond as quickly as you can. In the background, they are collecting data and batching them up and then sending them off to Graphite or whatever system that you're using to actually monitor your application. And with Lambda, you also lose this ability to do background processing. Besides a few things that the platform actually does for you, everything you do have to be done as part of your application. When an event happens, a request coming in, everything you want to do have to be done inside that invocation. Another interesting thing that happened is that before we were writing applications that runs on servers or containers, we are handling the concurrency inside applications. So I'm building an API, and this API is going to handle X number of concurrent requests, or inside my code so that my application is handling that concurrency. And when I move to Lambda, that concurrency has now been lifted up into the platform and handled by the AWS already. So when there are multiple requests coming in to hit the API, well, AWS is going to spawn multiple instances of my function to handle those concurrent requests, which is great because it means my code is now drastically simplified. Writing highly performant and correct multi-threaded code is very, very hard. But at the same time, we also lose something in the process, whereby before we are able to collect a lot of monitoring data about application at the instance level. So you have one server running many concurrent requests, and you can collect all the information about all these different concurrent requests with your agent. But now the best you can do is collect them at the individual concurrent executions. In this case, that means that you're going to have lots of different agents collecting information and sending them to your monitoring system, which is going to mean that you're going to create a lot more traffic to those systems that you're depending on. So those systems, those vendors, have to be able to handle a much higher load. And I've worked with vendors in the past whereby the more load you throw at them, you end up having to run your own aggregate servers in the process before you send them requests to them. So that's the problem that many of the vendors now have to solve, because we are going to give them a lot more concurrent requests into from our Lambda functions. But you say, well, that's fine. That's an easy problem to solve. In that case, when my function call starts, so the first time my function runs after a container is created, all I'm going to do is I'm going to collect data, and I'm not going to send them every single time, and then occasionally I'm going to send them in a batch. Problem solved, right? Well, the problem comes that when your traffic goes up, Lambda is going to auto-scale to handle the increase in traffic. And once that traffic goes away, then the containers that are now idle will be garbage collected by the system. So along with any data that you've batched up but not yet sent. So when you're doing this sort of batching and sending, then there's a very good chance you're going to lose data when your containers get garbage collected. And you say, fine, in that case, I'm just going to do the simple thing. I'm going to send a request to Graphite or whatever at the end of every single request. Well, the problem is that, as I mentioned before, we don't have background processing anymore. So if I'm building an API, then API gateway doesn't get a response back from Lambda until everything I'm doing in the function has completed, including sending any custom metrics or any monitoring data at all to my third-party providers, or it could be CloudWatch in this case, which means it's going to increase my latency, so my users have to wait longer to get a response back from my APIs. So now I'm getting caught in this catch-22 situation whereby if I'm batching data and sending them occasionally, then I stand to lose data. But if I'm sending data eagerly, then I can add latency to my user, my critical path. And then another trend we notice with serverless is that people are building more and more systems on top of events. Architecture increasingly being driven by events. And we find lots of Lambda for invocations that are trained together by asynchronous event sources, such as a write to DynamicDB triggers an event into the DynamicDB streams, and then that triggers a Lambda function to do additional processing. Or maybe someone publishes a message into SNS, or maybe from an IoT device, you publish a status update to IoT message hub that triggers a Lambda function to do some processing and handle that event. And of course, trying to trace what happens in the system the whole way through across these asynchronous events are much harder compared to tracing synchronous direct API to API communications. So those are just some of the challenges that the serverless paradigm introduces to the way that we use monitoring and observing our systems. But you still very much can implement all these different things that we talk about in terms of how do you observe, make your system your application observable. In my previous role as a principal engineer at The Zone, which is a sports streaming platform, we had over 1 million concurrent viewers, and we had a serverless first mentality where we had hundreds and hundreds of functions, maybe over 1,000 at this point, managed and run by many different, over a couple hundred engineers across multiple data centers and different regions and countries as well. So lots of people are working on many different functions. They have to run them at scale. So we had to find a way to make sure that everyone is doing the right thing, that they're able to monitor and operate the service architectures in production, and including using PagerDuty, so that when things go wrong, the right people are woken up to handle that issue. So I'm going to talk about some of the things that we have done, some of the tools that we have built and open source as well in the process. So in terms of logging, one of the things you get out of the box is whenever you write to standard out from your function, it will be collected asynchronously by the platform and shipped to CloudWatch logs. Again, asynchronously without adding latency to your function's invocation time. And as part of that, you also get some useful information such as UTC timestamp, unique request ID, and as well as your actual log message itself. And once your log messages are collected into CloudWatch, the way things are organized in CloudWatch logs is that every function has got a matching log group inside CloudWatch, and inside that group, you have one log stream for every container that Lambda is running for your function. Now, CloudWatch logs group is pretty great place for staging your data, and you get it out of the box, but it's not good for searching because you can't search your logs across multiple groups at the same time. So if I want to find out all the places where there's this particular string appear in my logs, I have to search them in the logs for every single function separately, which is, of course, not going to work very well when you've got many, many functions. So what we're supposed to do is that they'll go to the console, they'll select a log group, and they'll say action, and then they want to stream the logs from CloudWatch logs to either Lambda function or manage the Amazon Elasticsearch service. And in the case where you want to stream your logs to a Lambda function, then from there you can ship your logs to whatever other service that you actually want to use, which is great. But one of the things you need to keep in mind when you do this is that CloudWatch logs itself is an async event source for Lambda, which means if you're sending a lot of logs to CloudWatch logs, then it's going to try to run many concurrent instances of that same log shipping function. In this case, I've got in my region, I'm running loads of Lambda functions to serve my business critical APIs and services, and they're going to be writing to the CloudWatch logs. So in addition to the concurrency I'm using for the business functions, I'm also going to be using a lot of concurrency in my region to ship logs to my log aggregation service. And with Lambda, you have a default limit of 1,000 concurrent executions in the whole region. So so this additional load might end up pushing you much closer to your regional limit. And if you are just unlucky, then when the maximum concurrency is reached and exhausted, then any function can get the throttled next time Lambda tries to run it, which could be your business critical function, which means the concurrency you're using for shipping logs can actually start to hurt you in terms of the critical path. So at scale, what we can do is, okay, you know what? I can set a concurrency limit for that log shipping function, but then that means if that log shipping function keeps getting throttled, then I can also stand to lose data. So at scale, a much better way to do that is to subscribe your log groups to a Kinesis stream first, and then subscribe your log shipping function to the Kinesis stream, and from there you can ship your logs to wherever you actually want them to go. And the reason why it's a better approach is because with Kinesis and Lambda, you can control the concurrency for that Lambda invocation using the number of shards. Every shard in the Kinesis stream has one instance of your Lambda function as well. So if all my logs are streamed to a Kinesis stream with 5 shards, then I know I will have 5 concurrent executions for that particular function. But every time I create a new function, Lambda is going to create a new log group for me. I really don't want to have a manual process to then go into the console and click subscribe every time I create a new function. So what you can do instead is use CloudWatch events, or in this case, you can the new rebranded name is the event bridge. You can then create a new pattern to say anytime the create log group API is called against CloudWatch logs, please call my Lambda function, which will then subscribe this newly created log group to my log shipping function. And if you don't want to do this yourself, then I also publish a serverless application, which you can go to the repository.aws.com, and then you can deploy that from the console, or you can use the CloudFormation or SAM or the server framework to deploy this for you, which would every time you create a new log group, you will automatically subscribe it to an ARN, which can be a Lambda function or a Kinesis stream, and also looks after all the existing log groups that you already have in your region as well. And equally, you don't want to keep the logs in your CloudWatch logs forever, because there is a cost associated with that. So there's another application you can deploy into your environment, which then automatically set the retention policy for those log groups that you have. In terms of the actual outputs that we generate from our application, the single most useful output for non-functional reasons is having logs. But one of the things I keep seeing is that we are not writing logs in a structured format so that they're easily parsable by applications, so that they can then add a lot more context to our logs, so that when we can easily search and filter them. We've learned a lot in the past about why structured logging is important and how to do it well as well. And for Lambda, because you get log collection out of the box, you just write to send it out, or we find that a lot of companies now are forgetting the fact that actually, you know what, structured logging is still very useful. In this case, instead of having just a message saying calling API B and no context around what's actually happened, I can use structured logging. I can include a lot more information, including correlation IDs and other things in that log message. But what I do find is that many of the traditional loggers that's available to me for Node.js or for other languages, they're just quite heavy in terms of as an abstraction. And for Lambda, I also don't want to have very big libraries, which has got lots of dependencies, so that increases my code start time as well. So I want something that's really lightweight. So at the Zone, we built some tools called the Lambda Power Tools, and it's now open source as well, including a very simple logger, which just gives you a very lightweight abstraction layer that supports structured logging with JSON, as well as the ability to control log level via environment variables. And we see how that's important later on as well. In this case, all of our logs is going to be written in a structured JSON format. And when it gets shipped to, say, Logs.io or whatever log aggregation service you want to use, I can then very easily filter my logs by different fields once it ends up in an elk stack somewhere. One of the downsides of having structured logging is that, well, you do end up writing a lot more data to CloudWatch logs. And again, CloudWatch logs has a cost associated with that. You pay 50 cents per gigabyte of data ingested, and on top of that, you pay 3 cents per gigabyte that's been archived in CloudWatch per month. That's where the automatically updating retention policy is important there as a cost saving exercise. But 50 cents per gigabyte, that may not sound a lot, but when you consider that a Lambda function, a 128 meg function, 50 cents can actually get you more than 1 million invocations. So comparatively, CloudWatches can be actually quite expensive. And it's actually quite common for me to see customers who spend a lot more money on CloudWatch logs in production than they do on Lambda and other services. Especially if you're logging at debug level in production, those costs can really quickly start to pile up. So that's a very important lesson, is don't log debug level when you go to production. However, because in production you don't have any debug logs, so that when things actually go wrong, this has happened to me quite a few times in the past, whereby I know I can figure out what a problem is because I've got debug logs for that, but in production, we don't log a debug, so I have to go back to the application, change the log level, redeploy, collect enough logs to figure out what's going on, fix the problem, and then redeploy with the fix, as well as to disable debug logging again. And when you got up to log again, and then when you got application that's not just a single function, and you got lots of functions talking to each other, then that means you may find out there's an error down here, but the problem might exist somewhere down there. So in this case, you're going to have to enable debug logging for a lot of functions just to get a complete picture, which of course is going to massively impact you in terms of your mean time to recovery whenever a problem happens. But that's actually a really happy compromise between having no debug logs at all in production to having everything, all the debug logs, and costing you a lot of money when you can just sample a small subset of the debug logs, say, for 1% of the transactions you have in your system. So one of the ways we found to do this is using middlewares for Node.js functions. That is a middleware engine called MIDI. And with that, what we can do is we can have a middleware that wraps our function code so that before my code actually runs, I can change the log level for my logger to debug. And then after that, I can restore the log level to what it was previously. And I do this, say, for 1% of the invocations. So that 1% of the time, I'm going to have debug logs for my functions. But the rest of the time, I will just be logging as, say, error. And this is only possible for us to do because, again, concurrency is not in my code. I can very safely modify global variables without having to worry that, okay, I changed this code here for this request, and that's going to impact all the concurrent requests that's happening in my code. Because with Lambda, my function is going to process one request at a time. So in this case, our middleware is very, very simple. Before I run my function code, I'm going to check, should I enable debug logging for this invocation? If so, I'm going to enable debug logging, and afterwards, I'm going to roll it back to the previous log level. And whenever a function errors, I also want to capture the invocation event itself and include it in a log message so that I can then go to my logs and collect the invocation event, and then I can replay the invocation locally to try to simulate what a problem, where I can then attach a debugger to the code so that I can step through the code to see where the problem actually is. And in this case, we also want to make sure that when we make a sampling decision to enable debug logging at, say, the first function that's at the edge, that decision is then passed along to all the other functions so that I don't get, say, debug logs here but not here, so that I can never get the complete picture for what happens within one transaction. So instead, we'll be sampling debug logs at the whole transaction level, including for the whole entire call chain, including functions that are invoked via asynchronous event sources, as well as those that are invoked synchronously. In this case, we also want to track not just a single correlation ID. We want to be able to allow the developers to add other correlation IDs they want to include in their logs, such as order ID, session ID, and so on. And we also find that it's very useful for me to see where the request came from in terms of what the user agent was. Where for the initial request, when I'm looking at the logs for a function, there's several hops down the line behind, say, SNS or SQS. Again, we are taking advantage of the fact that within one function, within Lambda, our invocation is handling only one request at a time. So in this case, I can store my correlation IDs inside global variable, and we give you a nice little library to give you some very simple API for adding and getting the current set of correlation IDs. And again, we're using middleware so that before your function code is called, our middleware is going to inspect the invocation event, and it's going to figure out that, okay, this event is coming from API gateway, so I'm going to extract the correlation IDs from the HTTP headers. And if the event is coming from, say, SNS, then I know I can extract the correlation IDs from the message attributes and make it available for you so that anytime you log in with our logger, those correlation IDs will be automatically included in all of your logs. And so in this case, we are using the middleware to extract the correlation IDs, and then we're going to reset at the end of the invocation. In this case, we also have a bunch of libraries that also supports when you send an HTTP request to another endpoint, they'll automatically include those correlation IDs and forward them on. We support a number of different event sources, from API gateway, SNS, SQS, to step functions and direct Lambda invocations. And in terms of the logger, you're also going to include all the correlation IDs that you have recorded for the current invocation. And whenever you make an outbound request, those correlation IDs are also automatically included, including when you're sending requests to, say, SNS or SQS, we automatically include the correlation IDs in the outbound message so that the function on the other side will unpack them and include them in all of their logs as well. So that you don't have to be consciously remember to extract correlation IDs and include them every single time. In this case, a request comes in from API gateway. We're going to use the request ID for the first invocation and use that as a correlation ID. And then when we make a request to another API, the tooling will automatically include those correlation IDs as the headers going to the other API, so that the function on the other end will unpack them and include those correlation IDs in all of its logs. And in this case, you can see that we've got some correlation IDs as initialized, but we also have a couple of additional correlation IDs that you can set in your function, and those correlation IDs are then forwarded to every other function after this, from this point on. So again, the tools are available and open source and on GitHub, so you can download them and play around with that. And we support a number of inbound invocations, event sources, as well as outbound targets. And this middleware also supports sample logging and a bunch of other things, including detecting when you've got a circular invocation, when you get caught inside an infinite loop, as well as when your function times out. Make sure that we write an error log, which you don't get by default. And we spend a lot of time, quite a few teams spend a lot of time trying to figure out why they're seeing a spike in errors when they don't see any error message in the logs. And in terms of monitoring, you get a number of metrics out of the box, including invocation count, invocation request latency, throttle count, error count, and so on. But remember, we don't have background processing anymore. So if you want to call custom metrics from your application, then you kind of have to either go directly to CloudWatch or whatever system you're using, and that's going to add latency to your functions. So one of the things that one of the workarounds available in this particular space, you may say, okay, well, that's going to take, 10 milliseconds, so it's no big deal. But remember, when you got microservices, oftentimes you got one service calling another one, so those additional 10 milliseconds per invocation can very quickly start to compound as well. And Amazon a while back found that every 100 milliseconds they add to the user-facing latency actually cost them roughly 1% in terms of sales. So those additional latency you're spending to send metrics can actually start to hurt you in terms of your revenue. So one of the workarounds available in this particular space is that you can instead, because you can instead write those custom metrics to standard out, and because standard out are captured and shipped to CloudWatch logs asynchronously, you can then have your function to then process them and parse them and turn them into custom metrics and publish them to CloudWatch if you're using CloudWatch as your metric system. In this case, I also just published a new serverless application yesterday, which allows you to do that so that you can write your custom metrics in the StatsD-like format, and then this application can then process it and turns them into custom metrics in CloudWatch metrics. In this case, you're going to add additional delay to see your metrics, so that's the downside of that. But at the same time, you can remove all the latency overhead associated with publishing custom metrics from your Lambda functions. So I think this is important to consider when you're building lots of APIs with API Gateway and Lambda, because again, those extra things you're doing as part of the invocation have to be done before API Gateway gets a response back from your function and can respond to your caller. But if you're just doing background processing, processing events from Kinesis or SNS or SQS, then maybe those extra latency is not that important because they're not user-facing. Then at that point, maybe you don't want to go through this async processing route, and we just send the custom metrics to CloudWatch directly from your function. Once you've got all your metrics, the system ones as well as the custom metrics, then don't forget to create the dashboard and make sure that you set up alerts so that when something goes wrong, you will notify someone via PagerDuty, for example. And in terms of tracing, AWS has got X-ray service out of the box, and with X-ray, you can actually, especially if you take the time to instrument your code, you can see exactly what's happening inside your function, and also when your function calls another API with Lambda behind it, then that everything gets included in the same trace. So I can see in this case how much time is spent talking to DynamoDB or S3 and so on, and I can also see what happens in the second function behind API Gateway and how much time that contributed towards my overall latency for that first call. And with X-Ray, you also get this service map view where you can see from your function what are different things it talks to and the average latency for those different things, as well as the health for those services as well. One of the downsides with X-Ray is that it doesn't support async event sources. Actually, saying that, they've just kind of announced X-Ray support for SNS, but that's not yet available yet. They've just announced it recently last week, but that should be coming soon. Still, it doesn't support other async event sources such as SQS or Kinesis and so on. And also, it doesn't support any other non-AWS services. I know many customers like to use Auth0, which is a great alternative to Cognito. And this is a space where you find quite a few, newcomers into the scene, including Lumigo, who has built solutions that focus around monitoring your serverless application at the transaction level. And with Lumigo, you can also see the estimated cost for your user transactions so that you can find out, which transactions actually cost you more money so that you can focus on optimizing for cost when optimizing those functions, those part of your system when you want to bring down the cost for your overall system. So that's everything I've got to say on this topic, and I guess in terms of takeaways, make sure the most important thing you're doing and the simplest thing you're doing is writing your logs in a structured format. And instrument your code so they can take advantage of services such as X-Ray, and also make sure that you have got, you build tools to make it easy for your developers to do the right thing by default, or try out the Lambda Power tools that we put together for Node.js functions from the zone. And with that, thank you guys very much for your time. And if you want to get in touch with me, I'm available on my blog, on Twitter, LinkedIn, and the usual places. Thank you very much.
Well, a fascinating talk. Thank you very much for that. Any questions? Surely you've got a question. Great, excellent.
Wow, what a good talk. In the very early days of the internet, I read that people will not wait more than 10 seconds for a web page to render. That statistic you showed for Amazon, funnily enough, works out at 10 seconds you lose 100% of your revenue, and they've just reconfirmed it.
Yes, certainly. Well, one of the things that people also always talk about with Lambda is the cold start. And one of the misconceptions there is that actually with Lambda, cold starts is a thing, sure, but with Node.js functions, with a small amount of optimization, you can get Node.js functions or Python and Go functions to have a cold start time that's well within a acceptable range in terms of user-facing latency. I see many Node.js functions with a cold start latency of about 500 milliseconds and below, with a very small amount of optimization. But of course, if you want to use Java or .NET Core, then the life is a bit different. So when it comes to building user-facing stuff like APIs with Lambda, don't use things like Java or Node, Java or the .NET Core for the moment, because of the fact that it's going to add quite a bit of latency. Got a question there?
Yeah. Hi. When you started the problem statement, you said if we send logs in a batch, you will lose logs, or if you send eagerly, you will have added latency.
Right.
In your experience, if you send those logs asynchronously, it's like fire and forget. Is that really added a lot of latency, or what is
so you're saying that we're going to send it eagerly, but we're going to send a fire and forget instead of waiting for a response? Yeah. Potentially, but the thing is for most of the languages, at least, you don't actually know when the data has actually left your. The API doesn't let you know when the data has actually left your buffer. Even though you fire and forget, and you continue, you finish the invocation, fine. But there's a very good chance that the data hasn't actually left the container. It's still in the container, the API is returned, but you still end up losing data because of that.
Okay.
So even though, I've also used services where I can send stuff over UDP instead of HTTP. Those are a lot better, but I still have to wait for a flush, and it does add a bit of time still, but it's a bit better.
Okay, thank you.
Okay.
Question at the back.
Right at the back.
So you've advocated using structured messaging. Have you looked at strategies for reducing the size of the payload? Because I noticed some of the tags are really long.
Yep.
I don't know whether you can do things like substituting simple single character tag names and then processing those. And also the error messaging. Have you done stuff about going through the source code to substitute strings for code or something, and then you could reconstitute that later? Just any thoughts about that? So.
Yeah, so rather than trying to do some clever things with the log message itself in terms of structure, I actually quite like JSON because it's really human readable. Instead, I think it's better to just do sampling. So instead of having really this big payload all the time, we just have a very small percentage of them most of the time. But that's something that I've been advocating to a lot of sort of serverless monitoring tools vendors for their messages, rather than recording a huge amount of data every single time. They can use something like a binary format, and they can also just don't record every single the same things all the time. Because if you look at some of the vendors available, they actually have support for async collection, so they write their trace segments to your logs first, and then they've got a function to process it afterwards. And if you look at those data, one vendor I looked at, they are recording 16 kilobytes of data for every single invocation, just a hello world. And most of the data is just labels and repeated fields like function name, memory, the same thing, just never change for the same function. So for those guys, I've been advocating for a while that do some optimization with the message they're sending, because I'm going to end up paying a lot of money for CloudWatch logs because of the data that you're publishing on my behalf. So that's the only place where I've tried to advocate for something more efficient rather than JSON. But for my application logs, I think JSON is fine. I just apply sampling instead.
Okay, thank you.
Any other questions?
Okay, one more. How are we doing on time?
Let's say I have a whole cascade of Lambda functions and a sort of a complex network.
Right.
Do you have any suggestions if I wanted to sort of run integration tests against them? I catch an error in a log, and then I want to turn that edge case into a test in my code base. Any ideas around it?
So I guess it depends if your execution flows across just the service that your team owns, or does it flow into other team systems? Because if it's just within your team's boundary context, then I'm actually quite happy to normally run end-to-end tests for my application, so that I would call the API to do something, and then I would inspect that some other thing happened afterwards within my SLA. So that's what I would do. But if you started going across to other teams' boundaries, then that's a bit different, because that means I have to test someone else's code and bring them into my environment. Those other things start to get in the way of doing that. So I typically just test to the boundary of what I control.
Okay, great. Final question.
Thank you very much, Yan. Great talk. I was just wondering, is there any way we can get access to your slides?
Yes, I will publish them to SlideShare, and then I'll share on Twitter and on the Meetup page as well. Cool.
And also, this whole talk has been recorded, so it will be on our YouTube channel very shortly. So, round of applause for Yan for a fantastic talk. Thank you so much.
Thank you guys very much.